Welcome to the Distinguished Lecture Series at the Scientific Computer and Imaging Institute. Now that Valerio is here, we can start. And there's a couple chairs over here if you want, or some folding chairs. We are very honored to have one of the world's leading visualization researchers joining us today. Jack van Wyk from the University of Eindhoven is definitely, in my opinion, one of the our greatest researchers, both in scientific and information visualization. Jack has been honored for his research with an IEEE Technical Achievement Award, which is the highest honor in our field for visualization. And I'm really pleased that he would travel all this way from the Netherlands to be with us for a couple of days to share with us some of his research. Jack is very well known for his work in many different areas of visualization. I think early on he did a lot of work in different types of flow field visualization. More recently, he's been spending his time looking at different information analysis and visualization techniques. And I've asked him to give us an overview of some of his research techniques in information analysis and visualization. So please join me in welcoming Jack van Wyk from Eindhoven today.
Thanks, Chris, for the introduction, and many thanks for inviting me to come over. It's for me a great honor to be here. Utah is kind of holy ground in the world of graphics and visualization, and I'm always have been extremely impressed by the Ski Institute and all the great people that work here and all the wonderful work that's going on, and I really look forward to talking to you in the coming few days. Okay, the talk I want to give, it's quite a simple format. I simply try to show you a lot of different things we've done. I could pick one or two or three things, but, well, maybe you don't find them interested, so I simply try to squeeze in as many pictures, videos, demos in 1 hour as possible. Okay, there's only one problem. What kind of title do you give such a talk? This time I picked InfoVis from Eindhoven. Well, even that one is not really correct, because it's not everything is from Eindhoven strictly, and also it's not only InfoVis. Another attempt to a title was this one, Science and Art of Visualization, but yeah, it's somewhat bombastic, this one. But there is a story behind this, and I'd like to share it with you. As you all know, visualization is quite simple. You take a lot of data and you try to make a picture that someone can do his work properly. The fun part of visualization is that it's not only science, but also there's quite some design in it and maybe even some art. Now, how do we come to optimal visualizations? The royal route, of course, is to use user-centered design. Yeah? Users are extremely important, and each step you make, starting from the problem they have, the prototypes you make, the requirements you set up, the evaluation, you involve the users and ask for their opinions. And it leads to new methods, techniques, tools, programs, etc., etc. But that's not the only way. Now and then I do something which I call curiosity-driven visualization. It works as follows. Forget about user-centered design, forget about the users, and just do everything yourself. Yeah? Define your own puzzle, you define yourself how to make pictures, and you judge the pictures also yourself. And now we come to the art of visualization. If you look at this mode of operating, it's suspiciously like an artist is doing his work. Good. I'd like to show you some InfoVis, a few things on visual analytics. Recently, we've become more and more involved in GeoVis. I'll show you one demo concerning FlowVis. The technique is old, but the demo is somewhat newer. And then finally, I show you some things I really find totally exciting, and that's some mathematical visualization. Okay, I started in '98 with this question: was your hard disk full? That's a good type of question to do visualization for. It's a fuzzy question, and using standard tools it's quite hard to find an answer. So in about '98 we developed a new technique called cushion treemaps. And here you see a picture of my hard disk at this very moment. I assume everybody knows roughly what a tree map is. The rules are simple: each rectangle is a file. The bigger the file, the bigger the rectangle. Files in the same directory are close to each other, and the color shows the type. And now, for instance, here you see that there are some big animations. The orange ones are animations, purple are archive files. Here you see, for instance, the Microsoft Office part. Here you see the Windows part. These are my documents. And you can use such a tool to find out where you're wasting space and where the problem is. There are some options here. For instance, if you're curious what a file is, you can open it. Then you see, in this case, a picture. You can zoom in, see more detail. And there are different ways to tune the layout. Here, for instance, you have a so-called squarified layout, in which we try to make the rectangles as square as possible, and that makes it easier to point at them. Okay, this is a tool called Sequoia View, which you can still download from the web to have a look at your hard disk. This had one interesting result. In 2005, a master's student made a generalization of this technique. We started to cooperate with an external consultant, and this led to a spin-off company. And they now provide a variety of tools and services to visualize data. But also, as an academic, it's very interesting to cooperate with such a spin-off company, because then you learn what problems are in the real world. Back to weird stuff. Besides those cushions, there are other ways to visualize trees. After we did the Sequoia View thing, we did botanical visualization based on a simple idea. There are a lot of techniques around to generate botanical trees or models of botanical trees, and can you apply them to abstract data as well? Well, this gives pictures that looks like this. This is again my very hard disk at this very moment. The rule of the game is here that each branch represents a folder. Each sub-branch represents a subfolder. You can see we have documents and settings. This is the Windows one, and it goes on. Here's the installer. Now the files are represented as little cones, and a bunch of files that are in the same folder are put on one of those spheres. And for instance, let's have a look. You see the one with all the red cones, that represents one folder full with images. There are many options to play around with. For instance, this is something called phyllotaxis, which has a strong influence on the shape of your tree. It tells you something about how each new branch is rotated. So here you see an angle of 0. If you look at it from the top, it's clear. You can also increase that angle, thereby change the shape. If you use, for instance, 180, you get a structure where you have this left-right branching. And you see that now you get a lot of collisions between the branches and the spheres. If you use 222, then that's very rare, and you get a nice distribution of stuff through space. We lean on this heavily on those botanical algorithms, and this is typical one trick from this botanical world, this golden ratio here in choosing this angle. Okay, when I started I thought that InfoVis world is simple. You have trees, you have networks or graphs, and you have multivariate data. If you try to do things for the real world, you find out that very often it's a mix of these, and it becomes more interesting. For instance, a combination of trees and graphs is quite ubiquitous. Think of a group of people that work together in companies, and maybe these companies belong to holdings, or you can think about cities and continents and countries. And now suppose that people are emailing each other or having phone calls. That gives you a graph on top of this hierarchy. And obviously also in software engineering this is quite ubiquitous. You have a number of packages that contain classes which contain methods. Now suppose all those methods are calling each other. And again you have this pattern of the graph on top of a tree structure. You can visualize that in different ways. Well, that's of course one of the intriguing parts of information visualization. The data itself is abstract, so there's still many possible choices you can make for the visualization. In the first case, we use something called a matrix representation, which is quite straightforward. Suppose you have this little node link diagram, then you can show the incidence matrix. So for instance, D calling D is represented by this little gray square here, and then you can look at things. It's work of my former PhD student Frank van Am. Here you see a data set from a real world case, in this case a big software system from medical systems, Philips. There are 5 different layers in the 5 different levels in the hierarchy. In this case, layers, units, modules, classes, and methods. And in this case, the software architect was very interested in which cases do people conform to the specification, and in which cases do they not. So yet the actual calls were extracted from the system. The architect has given a list of what was allowed and what was not. It was not really thorough. You see, for instance, that on the diagonal, meaning things following itself, there are many red squares. But on the other hand, things like this are really suspicious. One disadvantage of such a matrix view is that the number of cells you can use is limited, so interaction becomes important here. And well, with this one you can zoom in quickly in and out. And move around. Here we added some extra visualization to show the size. And you see here that this particular part of the system is called by almost everything, and also that it's very, very big, so you can have some questions about the balance in the system. This animation, we had a separate paper on that, by the way, and for instance, if you know Prezi, the presentation program, it has used now the same methods of zooming in and zooming out. But just like with the trees, you can also do very different things. This is work of Danny Holton. I'll start up his demo separately. the same data set. Okay, here the hierarchy is depicted by those concentric rings. This is one layer separated in different units. In units you have little modules. To show the network you can draw straight lines, and in this particular case the direction is coded by the color. It goes from green to red. Found it always difficult to remember what the convention was for the direction, but then he told me that it works like this: if it's green you can move, and if it's red you have to stop, like a traffic light. More about direction in a few seconds. Well, obviously this picture is quite messy, so we invented a method to improve on this by bundling the edges. The idea and also the technique behind it is very, very simple. In the center here there is a hierarchy defined, and we use that to define some splines. Now we linearly interpolate between the spline and the linear version to get the desired amount of bundling. Another nice aspect here is that you can use it also for different tree visualizations. For instance, here you see a spherified tree map showing the same data. It looks somewhat more messy, but if you don't use the bundling, the mess becomes even much bigger and the whole picture becomes close to useless. Another tree visualization method is called the balloon tree, and you see how it works. It's simply circles inside circles inside circles, and again here the bundling helps a lot to remove the clutter. Let's see. Okay, in all those cases you expect there is some hierarchy, and in many cases that's the case. We also considered, can we bundle also if we don't have a hierarchy? Well, one way to do that is to superimpose a hierarchy on that, and people have worked on this. Here we tried to use a kind of physical model. We model all the edges as long springs that attract each other. If the springs are close, they attract, and in the end that leads to this kind of patterns. This is demography data from the US showing migration. The direction of the edges. Well, for this bundling stuff we use the green to red convention, but of course there are many other ways you can show the direction in an edge. Classic one is the arrow. You can play around with the lightness of the edge, from light to dark or from dark to light. It's not sure what's most obvious. You can also take such an arrowhead and stretch it, giving you a tapered edge. And this is quite intriguing one. Each edge is curved, and the curvature encodes the direction. If you use the convention that the direction is always clockwise, then this is a perfect encoding of the direction. At least conceptually. Now the question is which one to use. So we did a user experiment, so have a look. Which one do you think will be the winner? The tapering is the winner, yes. Here you see a little diagram in which we summarize the results. The tapering was clearly better than almost all other ones. There was only no significant difference between tapering and dark to light. But in some sense, the tapering and the dark to light are somewhat similar. Both start with something dark to light. That's the one on top of this. You see that if you consider this as, say, an anti-alias version of a thinning line, it would also be. The classical arrow was one of the losers. The test we did here was we showed graphs and then asked people are two nodes connected or not. And for that particular task, it's quite helpful if you quickly can see the path and also if you can see the direction for the complete edge. The problem of the arrow is that it only depicts direction from the beginning and the end. And, well, this curved one lost in a horrible way. This one is very not pre-attentive. You really have to think about, okay, clockwise, it means that this is the direction, and aha, so the edge is going this way. Well, here you immediately see what's going on. This is a nice example of the kind of traps we step in all the time. We come up with brilliant conceptual mathematical ideas, but in a lot of visualization, and especially also in InfoVis, the real bottleneck is your vision. You want to have things that are really pre-attentive and that you don't have to think about it.
A question?
Yeah.
So, how do you distinguish then some of these representations maybe just are at first? And maybe if you use that often, you get used to it and you get more efficient. Were you able to do a study that you looked at this in a more longitudinal way?
No, we were not. Yeah, I see your point, and I read that statement in many papers in which people have invented something new and the test showed it was far worse than what everything we've done. And okay, if you spend time on it, they claim you can learn it. It's true, actually. If you have time, you can learn everything. I show you a little miracle. What's shown here? Good. Yes. Wonderful. Without thinking, you can read this. Yeah? And we can do that because we have gone through a very long training period. So in the end, I'm pretty sure that you can learn to decode this and to understand it. On the other hand, you don't get it for free. Well, this one, okay, you can make a head start. And I'm sure that many of you will have this experience that your customers you work for are not willing to spend 2 weeks training to learn your visual encoding.
In as much as approximately 10% of the population is red-green colorblind,
Yeah.
have you had any reaction to, I mean, you could have chosen red and blue or something.
Yeah, definitely. Indeed, that makes it also very doubtful. And we could have chosen different things. Red-blue probably would be better. But one other problem with color here is that if you use thin lines, then it's getting harder and harder to see the color anyhow.
Yes.
So solution is to use thicker lines, and then you waste screen space. So yeah, color is somewhat doubtful. So the best way to do it is, in this case, simply to use the illumination channel. Okay, another perception issue. This was work of my PhD student Jing Li. well, in InfoVis we use glyphs and icons all the time. So one puzzle you can have is, suppose you have to design a sequence of circles like this, and now you want the circles to be such that each step between two pairs of succeeding circles is perceptually the same, so that you have a feeling it's a nicely balanced scale. Well, here you see 5 different alternatives. You see that now sometimes strange things are going on. For instance, here you definitely suddenly see a very big step, and well, it's not really simple to design a scale that's optimal. In this case, we did a lot of experiments in which we didn't ask people which scale do you like best, but we asked them to perform some tasks, like for instance, pick the outliers or count the outliers. And then we postulated that if the time they take is representative for the perceptual distance. These are the different formulations of the scales. And in the end, we found that this funny relation gave the best result. This is just a linear increase in radius. I think that this one is a linear increase in area. Exponential. Well, it was quite a surprise to us that it was not something like area or exponential or logarithmic or what you would expect.
What was the task to estimate just outliers, or do you estimate linearity of the underlying data?
Well, we did different things. We did do things like count the number of outliers. We did experiments like which type of glyph has the biggest fraction. So that were the perceptual experiments. But we also did, for this particular case, a separate set of experiments in which we asked people directly which, typically we presented 2 different scales and asked them which one do you like best for equal steps or for linearity or different things.
And
for
how
those
often
things,
this came out to be true?
no, for certain questions, other scales popped up better. So if you really want to have linear radius, you must have a linear radius. But this one was on overall still averaged on the different questions, still the winner. And certainly for the question on equal perceptual steps. Okay, if you know the field a little, you know that visual analytics is getting more and more important. Yeah. This is an earlier example I did in sort of visual analytics. It's about combining statistical methods and graphics. This was data about, in this case, number of people working at an institute. You see the data for one particular day. People start to come in at about 8. They leave at 5 p.m. In the afternoon, some people are working.
So what is the y-axis is power, I think?
The y-axis is simply a number of people.
Oh, okay.
Here you see 600. The data was measured by, because people had to clock in using a little card. Well, one way to visualize this is simply to show a lot of graphs. And then you see there's some bundle of graphs here, probably weekends. These are the working days. But that's not really clear. If you put in a little statistics, it becomes much clearer. Here I applied a cluster analysis, and in this case I show two clusters, the blue one and the green one. You see that the green one are the weekends, the blue ones are the working days, but there are also some days at random positions in the middle of the week. This is our King's Day in Holland, Liberation Day, it's a Christian holiday, another Christian holiday, Christmas itself, New Year. They pop up quite quickly. Here I show more clusters, and now you see, for instance, that on Friday less people are working. That's brown. You see that in the summer fewer people are working. And if you take the Cartesian product of that, Fridays in the summer, you get this blue cluster over here. One nice thing of using clustering is that you not only see the big trends, but also get some outliers. For instance, this purple one here shows you a special day, last day of the year, but everybody was motivated to work. But my personal favorite in this data set is this one. Here you see that suddenly people went home much earlier. Well, if you're from Holland, you immediately understand the explanation. This was December 5th, and then we celebrate Santa Claus. And everybody can go home 1 hour earlier to spend time with the family.
So what's the motivation to do this kind of revisions? To do a better management?
No, I did this work when I was not in Eindhoven yet, so this was the exception for my title. I was working at Energy Institute, and the reason to do this was to monitor energy spending. If you have an energy company and sell electricity to customers, it's important to have a good idea on what patterns are occurring, and if you can make special deals for people to encourage them to have certain behavior. But also, it is interesting to look at this kind of data. I once did an experiment with a colleague when I filled about just his data, and that gave graphs like this, only much coarser because there was only a difference between 0 and 1. But when we applied the clustering, then still you could see the patterns, and in some parts he was commuting, then he was sharing a car with friends, and well, all those patterns showed up quite early. So I think for forensic type of applications, this approach can also be interesting. This is also one of my personal favorites, because it shows that often you can get away with extremely simple, trivial visualizations. This is just a graph, that's a calendar. And people have used calendars for ages, so they're trained to work with it, they immediately understand it, and the whole visualization was made to be able to reason about this kind of patterns nicely. It's nicely that all the Saturdays here are in one row, that all the months are closely together. Well, proof technology, that's ideal to work.
My mind keeps going back to your power of 2.5. And that's the radius, right? So it's not clear if the radius ratio is squared, that's only linear in the area. So are we reacting to area or to radius? So I would think this is super linear, in
Yeah.
the sense of area.
I always mix it up. I always get it one direction or the other way. It's better to talk it afterwards than I try to reconstruct which way it goes.
Anyway, it's a little more complicated than one might just glance at.
Some slightly more recent work we did, and it shows another aspect of visual analytics, and it's related to a lot of the nice work that's going on here. If people look at visualizations, they get insights, and you want to help them to share the insights. So, Yudendra Srinivasan, PhD student, made a very nice system to enable people to capture their knowledge. The final design we came up with was incredibly simple, but we believe it can be quite effective. You see data visualization, in this case straightforward scatter plot with some selection options. Here you have a little kind of mini PowerPoint in which you can define boxes and circles and draw some arrows. Now the trick is that each time you introduce such a graphic element, say a box, then the system remembers what kind of visualization is shown here. And if you browse through the data and each time you find something interesting, you put a little box over here. In the end you have your own personal notes and you can rearrange them and try to bring some structure in it. And then by clicking on one of those boxes, you immediately get your visualization back. Highly simple, but the real nice thing here was that people started to use it in different ways than we expected. We thought about enabling them to draw their own mind maps, but people also used it just as a little memorization issues, or even some people used it as some kind of little custom interface so that they could quickly change the view over here. Well, so we were happily surprised by that. Okay, some work we did on geographic visualization. Moving data is getting hot these days, that's a lot, and it's a fascinating challenge to visualize them. Here you see my country, the Netherlands. This is the North Sea, this is Rotterdam, Eindhoven. And here you see vessel traffic plotted. Each vessel these days has to have a little device, kind of GPS device called an AES device. And you can capture these data and collect them. If you draw them simply as tracks, then you get a picture like this, which already shows the big lanes in the sea. But you can get a better result by putting some graphics here. The idea is quite simple. We take the trajectories, we convolve them, and we do that twice. Once with a big kernel, and it gives you the big patterns. Also once with a small kernel, and it gives you the more narrow patterns. If you look at those pictures in close-up, there's a lot of detail that can be seen, as well as the overall overview. For instance, this is an anchoring place. There are ships located that are waiting before they can get inside the harbor. And, well, after some training, you can see certain patterns that are specific for instance, ferries or tankers and so on. This was one of my own hobby projects. It's about how to make a map of the world. Well, the best way to do that is to use a globe. Unfortunately, such a globe has also some disadvantages. If you want high detail, then the globe becomes quickly very big. So people have invented something else, which they call a map. If you have a globe, then you can depict the surface without distortion. If you have a circle on the surface of the globe, of the Earth, then without any distortion you can map it on your model. But things go wrong when you flatten this globe. This is the Mercator projection, for instance, and then you see that the shape of your circles is okay, but the circles get bigger and bigger very quickly. So we have an area distortion. We can get the area right by using, for instance, this projection, but then something funny happens with the shape. You see a lot of distortion of the circle into elongated ellipses. Well, I found a solution to cope with this and to get a solution without area and without shape distortion. Build up some tension. Of course, the only way to do that is too cheap. I called it myriahedral projections. The trick is to use interrupts. And if you use a lot of these, then you can get a projection almost without interrupts. Here I use fairly simple cutting patterns, cutting around meridians. This is an azimuthal projection. On one side you can also use other cuts. You get a pattern like this. Two hemispheres. You can see in the pictures if there's little distortion or not. If the gaps are big, then there's a lot of distortion. This is a projection on regular platonic solid with some little cuts also here, but very quickly you don't need them anymore. Here I apply the cuts dependent on the continents, and in the background there's some FlowVis technology here. Then you can unfold it in different ways. Here you see a cut in which I put the ocean central. And here another version where also Antarctica is cut. You can also do that in different ways by playing around with the weights for the algorithms. Here you see a version in which you see the continents and the oceans split up. You can simulate a kind of torn world with, for instance, Africa in the center. Myriahedral projections. I worked somewhat in fluid flow. Well, of course, the simple way to show fluid flow is to use arrows, but if you look in nature, then you see much more fascinating patterns. And also artists have a good feeling how they can visualize fluid flow. We developed something called image-based flow visualization, which generates textures, and it's so fast that you can play around with it. Last year I had an exhibition in a graphic design museum, and for that I had to demonstrate what flow visualization was about. So I made this one. This is some real-time flow visualization. You see what is going on. I take my picture and I use that to generate a simple potential flow. That means that every light spot becomes a little tornado, also every dark spot. And the flow is around contours of the luminance. And one of the fun things of the technique is that you can use it to generate quite a lot of different styles and patterns for the visualization. And also this kind of visualization is possible. Here I keep the picture the same, but the flow field is still influenced by what the camera sees. You can also make this more participative event. Here I use a matrix of a lot of little rectangles, each rectangle containing a little picture. Here I modulate the height by the strength of the flow potential. Oh. It's a very nice colorful setup here. Oh wow. Cool. Okay, last few demos about mathematical visualization. This is about knot theory, which is a part of topology. It's a nice puzzle. Here you have a simple mathematical knot called the traphoid. And now the question is, find some surface that has this knot as its boundary. Well, that's simple. You take a strip, twist it 3 times and then glue the ends together. And then you get this picture. But it's not a really nice surface. It's a kind of Möbius surface, which has which cannot be oriented. Suppose this is front and this is back. This is front and this is back, but we started with front, so something funny going on. So the challenge now is to find an orientable surface that's bounded by this knot. You see this traphoid. And here you see the solution to the little question. This is an orientable surface that is bounded by the knot. The fun part is that for any knot you can generate such a surface. It was an algorithm that was developed in about 1930 by a German topologist, Herbert Seifert. This is, for instance, a figure 8 knot, and he shows the surface. It also works if you have knots consisting of multiple links. This is the simplest link, called the Hopf ring. You see, it's just 2 rings that connect into each other. A very nice one is also this one. This is a very intriguing one. This is called a Borromean knot. It consists of 3 rings, and none of the rings is directly linked to each other. If you cut out one of them, then they fall apart immediately, but the 3 of them make it a knot. And again, you can find the surface that is bounded everywhere by this knot. And then you get this one. Somewhat wilder example. I made this, one of the reasons I made this was for kind of educational purposes. Not theory is a very good way to make people aware that mathematics is not only about formulas and algebra and things like that, but also about reasoning about shapes. You can define very hard questions without having to understand mathematics. For instance, when are two knots the same? Especially for this audience, I added some special features in this program. And here you see the close inspection mode of this particular Seifert surface. It still misses audio, and I have to put it in one day. Yeah.
So as you're constructing the surface, is it dependent on the original embedding of the map, or is your surface calculation independent?
It is dependent on the original embedding. Actually, I use certain. Here we go down. I use something called the braid notation, which is a notation for a knot, and from that I derive the surface. It's not 100% perfect because it does not always give you the minimal solution in a technical sense, but for many practical cases it does work. Okay, my last item I would like to show to you is about something called regular maps. It's also a concept from mathematics. A map in the jargon of surface topology is an embedding of a graph in a closed surface. And now a regular map is a kind of perfect version of that. In this case, all the faces are the same topologically, the vertices are the same topologically, and the edges are also the same. They are all transitive in the jargon. So that means if I would not color everything here, and I would put you somewhere on this cube-like shape, you would not be able to tell on which edge I am, or on which vertex or which face. If you look at that kind of shapes on a sphere, there are only a few of them. You recognize here the platonic solids. Now an intriguing question is what if we have more complex shapes with more holes, like a torus or maybe even more difficult shapes? Well, I'll show you a video with some examples. These are genus 2 objects, in this case 6 octagons. This is again genus 2, 12 octagons. Note that in all vertices the same number of faces come together. 64 triangles on a genus 5 shape. Genus 11. So that means there are 11 holes if you would flatten it out. Genus 4. This one is fairly easy to understand what the shape is. These are pentagons, topologically. If you want to have solutions for higher genuses, the shapes you can find are getting more and more complex. For instance, this is genus 13, or one solution for it. Genus 17. If you look carefully, you'll see that there is something of a tetrahedron inside this one. And the same holds also here. Genus 29. Okay, that concludes my talk. Question.
Yeah, I mean, what's intriguing about the platonic solids is that there's a finite number and only those finite numbers.
No, there are more, but for
And
simplicity.
my expectation is as soon as genus is greater than 1, you have infinite number of them.
Genus 1 certainly, but also for genus 0 you have an infinite number because
Right,
you
so
can use a beach ball also is a solution to that.
Then what makes these interesting compared to all the other infinite ones?
Well, in the other cases I showed,
Yeah.
there are not an infinite number of solutions, there are a bounded number.
Oh, they are?
Yeah, for
Okay.
genus 2 and higher, the solutions are bounded. They're known. Mathematicians have sorted them out using computer-aided group theory. And there's a long list with all the formulas for the solutions. But this formula is in terms of group theory and doesn't have any picture or geometry, which of course is not essential, but still if you want to have a picture, it's nice to have.
It would be interesting to use this to visualize the groups that are associated with them.
Yeah,
It's
but in
one
some
thing-
sense, these are
It's-
visualizations
yeah,
of
I'd
the
like to
groups that are
understand in what
associated.
sense is that how is the representation of the group associated with the visualization? Because that's always, it's easy to see the circle group, the cyclic group. When you get with these higher groups,
Yeah, you still can see the cyclic groups because each time you make a loop
yeah,
over the surface, doesn't matter where, there's a
there's a
you
cyclic
can
group
see that there's a cyclic group. But
So these interconnecting links must be some interesting.
Yep.
Yeah.
but there's much more detail in the paper.
Yeah, that's interesting.
All right, let's thank
Oh, I was not ready yet. My final sentence. Okay. I've shown you a lot of different examples of different types of visualization. I hope you enjoyed it and agree with me that this is all about fun fish. Thank you.
Time for a couple more questions.
Yeah.
So we sort of just continue the group thing. Are you actually visualizing homology groups or cohort groups, or what is the color corresponds to?
The color is related to a subgroup of the group itself. What I show is normal subgroups of triangle groups. Yeah. Yeah, I can show you some pictures later. It's about you take. No. See if I can quickly find a picture. This is not really the picture I meant, but this is how it works. This is cut out from a kind of Escher-like shape, which is a triangle group. If you would draw the little triangles inside this also. And you define a normal group by specifying some relators and that cuts out some part of the plane. Now the challenge is to fold that into a geometric surface. That's roughly what's going on.
There's much to think about from your presentations, lovely. I was trying to imagine what sector is picking up these techniques most readily, and my nomination is aviation. If you look at a route map, that can be really confusing, and they're beginning to use bundling to disambiguate, unless they really want to try to see how many routes they have, and they just need black ink. And also, pilot aviation maps use the sector maps because they want conformal maps, and they don't care if they come in little pieces as you program the globe. They've been doing that for quite a while.
And that's what they call charts, right?
Yeah.
Indeed.
Charts, exactly.
Now and then I get requests, and it's funny. For instance, someone from somewhere from Australia asked me for a special version where everything was focused on Australia, and he was working for the municipality of some city, and he needed that map to have people focus on, hey, we are the center, and there are quite some different ways to look at it.
All right, thanks.